Thank you so much for the kind introduction, and I appreciate ICP committee for giving me this opportunity to present our work at this webinar. I'm going to talk about QSM, qBOLD, and combined approach for oxygen extraction fraction OEF mapping. And here is the outline. First, I will go over two OEF methods without vascular challenges, QSM and qBOLD, and then I will talk about why and how we combine those two and how we improve the robustness of combined model against the noise using machine learning algorithms like CAD, CCTV, and deep learning net. Then I'll talk about the validation of QQ with calibrated fMRI and 15 PET. And at the end, I will go over our initial clinical experiences in stroke and multiple sclerosis. First, the two methods. In MRI, we consider blood hemoglobin effect on its signal. Oxyhemoglobin is slightly diamagnetic, and deoxyhemoglobin is a strong paramagnetic source. When tissue contains oxygen, deoxyhemoglobin in vein increases, MRI can detect this effect. Venous oxygenation Y can be defined with the deoxyhemoglobin concentration in vein. In this talk, I'll focus on two methods using multi-echo gradient echo dataset without vascular challenges, QSM and qBOLD. QSM utilizes phase information driven by susceptibility sum of blood and surrounding tissue. qBOLD utilizes magnitude signal decay driven by field variation within a voxel due to susceptibility difference between blood and the surrounding tissue. I will explain each in a bit more details and why and how we combine them. Well, let's start from this MRI signal equation, which I will use as a starting point of modeling. So M is an average spin distribution in a voxel, delta V is voxel volume, T is a measurement time, echo time, and T2 is signal decay rate caused by irreversible spin-spin interaction. Omega 0 is a main magnetic field strength, such as 3 Tesla. And lastly, B is the susceptibility field scaled to main magnetic field omega 0. This B is important in this talk. From this B, we can derive the signal decay by deoxyhemoglobin and susceptibility. And this average here is our average over voxel. Starting from this equation, we can model the deoxyhemoglobin effect in magnitude using qBOLD and in phase QSM. Let's talk about qBOLD modeling first. qBOLD was developed by Dr. Jablonski and Dr. He. It distinguished the magnetic field of B into two parts, mesoscopic field bmeso and macroscopic field bmacro. And the scale of mesoscopic field was much smaller than voxel size, so it's similar to vessel size, several microns. And this field is caused by deoxyhemoglobin in vein. And macroscopic field scale is larger than voxel. It arises from the susceptibility difference at air tissue interfaces and different tissue boundaries. And how can we distinguish those two? First, B is the sum of bmeso and bmacro. Since bmeso and macro are in so different scale, we can say the probability distribution of bmeso and bmacro is independent. So the interval can be divided into multiplication of two intervals. It means we can treat the signal contribution from mesoscopic field and macroscopic field independently. I'll talk about how the signal equation can be modeled with these two fields. For bmeso, the vessel is assumed to be long cylinder uniformly filled with the deoxyhemoglobin. We have analytic field solution for infinitely long cylinder shape, and from this field, we can estimate the signal drop by deoxyhemoglobin in vein, fBOLD. For bmacro, macroscopic field is assumed to vary linearly across voxel, then we can get the signal drop by this linearly varying field. Here, eta and M is the voxel spread function. It means if field varies linearly across voxel N, there will be signal contamination from neighboring voxels N. Let's take a look at fBOLD. The fBOLD is a function of venous oxygenation Y and venous volume V. And Fs here is a generalized hypergeometric function. It has a characteristic frequency delta omega. It is basically susceptibility difference between vein and the surrounding tissue. If vein is filled with a lot of deoxyhemoglobin, in other words, small y, the delta omega will be large and it would affect the signal drop a lot. Let's take a look at how the F-fold behaves. If the venous blood volume is fixed, smaller y, in other words, more deoxyhemoglobin, leads to more signal drop. If venous oxygenation is fixed, the greater venous volume, blood volume, the greater signal drop. The signal shows two signal decay pattern, the quadratic behavior in the short echo regimes and in linear behavior in the longer echo times. Due to these two different signal patterns, we can decouple V and Y. This qBOLD model made an assumption for simplicity. It assumes that non-blood tissue susceptibility chi-n is constant throughout whole brain, equal to purely oxygenated blood susceptibility. By doing so, qBOLD treats non-blood tissue susceptibility as a constant. However, this assumption might not hold because it ignores regional variations such as high positive tissue susceptibility in deep gray matters caused by ferritin and negative tissue susceptibility in white matter caused by myelin. We removed this assumption by combining qBOLD with QSM-based method. How about QSM-based method? QSM provides voxel-wise susceptibility, chi-voxel, and this chi-voxel consists of two contributions, blood contribution and non-blood contribution. From the blood contribution, we can estimate the venous oxygenation Y. The smaller Y means more deoxyhemoglobin in vein. It would increase total voxel susceptibility. This QSM-based method has an assumption to make the equation simple. It assumes that venous blood volume V is known based on the linear relationship between blood flow F and V. This relationship was derived from whole brain linear regression in healthy subjects. So it might not hold for voxel by voxel level and for patient cases. We remove this assumption by combining it with the qBOLD. Now I have explained two existing OEF methods so far. Let me explain why and how we combine these two. The QSM-based model is a function of Y and chi-n. It's a phase signal modeling, and venous volume is assumed to be known. On the other hand, qBOLD is a function of Y, V, R2, and S0. It is magnitude signal modeling. The chi-n was assumed to be constant. And QSM-based methods solve for chi-n, and qBOLD solves for V. So by combining those two models, we can treat chi-n, V as unknowns. Then we can remove unnecessary assumptions in each model. Also, we can utilize both phase and magnitude signal from the same data set. We call this combined model QQ. Here is optimization regarding model combination. The V is now included in QSM, and chi-n is now included in qBOLD. W is waiting on QSM term, which was determined by L-curve analysis. Here is oxygen extraction fraction OEF map from 3 methods. The QQ shows relatively uniform OEF map compared to QSM model. This agrees with the previous MRI and PET results. Here is the V, the venous flow volume map, and the QQ model shows similar values compared to two other methods. Then this is chi-n result. Both QSM and QQ method shows contrast between cortical gray matter and white matter boundary, and the values are similar. This contrast is consistent with the previously observed myelin difference between cortical gray matter and white matter. Here is corresponding CMRO2 map. In this CMRO2 map, QSM-based method shows a lack of CMRO2 contrast between gray and white matter. The error in gray and white matter segmentation or smoothing by minimal local variance assumption in QSM may cause these local underestimations. Second, qBOLD shows smaller CMRO2 contrast between gray and white matter than QQ. It might be because QQ provides the greater OEF than qBOLD. The greater OEF in QQ may be caused by the chi inclusion in QQ. Chi is greater in QQ than in qBOLD, which is assumed to be constant everywhere. To achieve the same signal decay, the greater chi-n, the greater OEF. However, this QQ model has an issue. It is involved with poorly conditioned non-convex optimization due to coupling among parameters. So it is sensitive to the noise. This slide shows how the results depend on the initial guess with noise. The gray box indicates the ground truth. We use different Y and V initial guesses, Y0 values and V0 values. Without noise, the result does not depend on the initial guess, showing dark blue from every initial guess. However, if we add realistic noise such as SNR 100 and SNR 50, when the initial guess deviates from the truth, the relative error increases. So we came up with a method to improve the robustness of QQ against the noise, cluster analysis of time evolution CAT. The basic idea is we look at the signal evolution with echoes. We cluster the voxels with a similar signal decay pattern together. Then we set a single parameter value for each cluster. In this way, we can improve SNR effectively. And for clustering, we use the X-means algorithm, a modified K-means clustering with providing an optimal number of clusters based on Bayesian information criterion. Here is a QQ with CAT optimization. In addition to cluster optimization, we added the physiological regularization. Lambda is waiting on the regularization, and the regularization is that the average of OEF over whole brain should be similar to the OEF value estimated from a main and draining vein, straight sinus. We compare QQ with and without CAT in the simulation in ischemic stroke patients and healthy subjects. Here is the simulation results. We simulated a stroke brain with low OEF area, presumably stroke lesion, and QQ CAT can capture low OEF regions in the all SNRs, whereas QQ without CAT does not show such pattern. And QQ with CAT provided more accurate OEF map with lower root mean square error. Here is a stroke patient result. QQ with CAT shows low OEF value regions, which is consistent with the lesion defined by an independent MRI contrast, BWI. And here is CMRO2 map, which is basically the product of OEF and CBF, and V map. And QQ with CAT shows smaller V in the lesion, which agrees with the literature, and R2 and high N map. Here is another stroke patient result. QQ with CAT shows low OEF area that agrees with a DWI defined lesion. However, QQ without CAT does not show such pattern. It is clear when you look at the histogram. QQ with CAT shows the strongest peak at OEF close to 0 in the lesion, whereas QQ without CAT does not show any specific distribution corresponding to the low OEF values in the lesion. Here is a healthy subject result. QQ with CAT shows more uniform and less noisy OEF map, good CMRO2 contrast between gray and white matter without extreme values, and V, R2, high N. Here is ROI analysis in cortical gray matter among 11 healthy subjects. OEF and CMRO2 from both QQ with and without CAT fall into the literature value range, and QQ shows lower OEF values. It might be caused by the greater R2 values. To obtain the same signal decay, the greater R2 leads to lower OEF. QQ with CAT shows a smaller V value than the literature, and whereas QQ without CAT shows greater value than the literature. Also, QQ with CAT did not show a gray and white matter contrast in V, unlike the literature expectation. This may be caused by limited clusters using only magnitude signal time evolution in CAT. To alleviate this issue and to further suppress noise propagation on OEF, we developed an algorithm called CCTV. We integrated tissue type information into CAT clustering by dividing each CAT clusters into 3 subclusters, gray matter, white matter, and CSF. Also, we impose total variation regularization on OEF, which reduces noise propagation. In healthy subjects, compared to CAT, CCTV shows a less noisy and more uniform OEF, and subsequently less noisy CMRO2, which agrees with the reference standard PET OEF. And the OEF noise suppression may be resulted from the using total variation. In addition, the incorporation of tissue type information in CCTV may lead to more robust model inversion and with improved initialization and improved inversion condition. The VMAP from CCTV shows clear gray and white matter difference, which also agree with the V contrast in the MRI literature. This may be caused by tissue type integration into clustering, which leads to more realistic V initialization and optimization. R2 and chi-N were not significantly different among three methods. In acute stroke patient compared to CAT and CAT plus total variation, CCTV shows less noisy OEF maps. Lesion OEF value appears similar to those on the contralateral side, which suggests the acute lesion tissue may be salvageable. In the subacute patients, CCTV shows an improved spatial overlap between low OEF regions and DWI defined lesion with less noisy OEF map. For instance, in a 9 days post-onset case, the low OEF region with CCTV largely coincided with the DWI defined lesions, whereas CAT and CAT plus TV do not depict low OEF values clearly in the lesion and show noise and artifacts in OEF maps. To measure detectability of lesion OEF abnormality, we measure the contrast to noise ratio CNR between the lesion and its corresponding unaffected contralateral side, with assuming the OEF variation within contralateral side originating from the noise. As shown in cyan blue, CCTV provides significantly greater OEF CNR in the subacute phase than CAT and CAT plus TV. This suggests a better lesion OEF abnormality detection with CCTV. The improved CNR may be resulted from improved decoupling between OEF and V, a crucial issue in qBOLD-based OEF modeling without very high SNR. The improved decoupling may result from noise propagation suppression into OEF using total variation and proper V initialization by integrating tissue type information in clustering. CAT and CCTV use a gradient-based iterative solver, which depends on optimization details such as initial guess and parameter scaling, and they are time-consuming. To alleviate this dependency on optimization details and to make the reconstruction speed fast, we introduced a deep learning approach, NET. Deep neural network has been applied as an alternative to the iterative method for solving inversion, as they can approximate any continuous function with a sufficient number of free parameters. So we use an established deep convolutional neural network architecture, UNet. It provided better lesion OEF abnormality detection with 150 times faster recon speed. So far, I discussed about constructing models and solvers. From now on, I'm going to talk about a comparison study of QQ with well-investigated MRI method, calibrated fMRI, and a reference standard 15 PET. As Dr. Weiss explained in the previous talk, calibrated fMRI models both signal a difference by R2 star change between baseline and respiratory challenges such as hypercapnia and hyperoxia for baseline OEF calculation. And CMRO2 is assumed not to be altered in hypercapnia. Here is OEF map from calibrated fMRI and QQ at baseline BL and hypercapnia HC in 2 subjects. Compared to calibrated fMRI, QQ shows more uniform OEF maps with relatively uniform OEF values in gray and white matter, which agrees with the reference standard PET. For calibrated fMRI, the OEF imaging quality is visually more variable than QQ maps due to low SNR in BOLD and CBF measurements. On the other hand, less noisy OEF map from QQ may have benefited from the usage of cluster analysis of time evolution, which improves SNR effectively. Both calibrated fMRI and QQ shows lower OEF map at hypercapnia compared to baseline as expected. Here are the corresponding CMRO2 and CBF map in the same subjects. QQ shows a good CMRO2 contrast between gray and white matter without extremely high values. QQ shows slightly decreased CMRO2 at hypercapnia compared to baseline. And please note that hypercapnia CMRO2 is identical to baseline CMRO2 in calibrated fMRI. ISO CMRO2 assumption is used. CBF is increased at hypercapnia compared to baseline as expected. The box plot shows RY analysis in cortical gray matter in 10 healthy subjects. At baseline, calibrated fMRI and QQ shows similar and statistically non-significantly different OEF and CMRO2. However, at hypercapnia, QQ shows a significantly lower OEF than calibrated fMRI, and QQ shows 17% decrease CMRO2 at hypercapnia compared to baseline, which is consistent with the recently reported mild CMRO2 decrease at hypercapnia. This observation may be an important contribution to the debate surrounding this ISO CMRO2 assumption employed in hypercapnia calibrated both studies. This comparison study of QQ with the established calibrated fMRI shows that OEF from the two methods are in agreement for baseline condition. Next, we compare QQ with the reference standard 15 PET in 10 healthy adults. This slide shows example OEF maps from PET and QQ in axial, sagittal, and coronal view in a subject. Both PET and QQ shows uniform OEF map and good agreements between scans and methods. In the regional RYs, such as cortical gray matter, white matter, deep gray matters, the OEF average values from QQ and PET are substantially equivalent, and this suggests that in healthy adults, QQ model generate OEF estimates in agreement with the reference standard 15 PET. QQ is now posed for a further evaluation in patients where OEF is likely to be regionally affected. Finally, I will introduce our initial clinical experience in stroke and multiple sclerosis. In the stroke, the OEF in the ischemic core shows a decreasing trend as time between symptom onset and MRI examination increased. There were significant OEF changes among three stages: acute, early subacute, and late subacute, whereas no significant changes were found for CMRO2, CBF, and ADC values among the three phases. In an acute ischemic stroke patient with 18-hour post-onset, the ischemic core red contour shows a slight decrease in OEF on average compared to the contralateral side. A mismatched yellow contour showed relatively higher OEF than the contralateral region, which may represent salvageable tissue. In multiple sclerosis patients, the rim, the QSM hyperintense area in the lesion, shows higher OEF than the core, which can also shown in this box plot in 80 lesions. This may be related to active inflammation by iron-containing microglia and macrophages in the rim. Compared to age-matched healthy adults, MS shows significantly lower OEF in all the RIs. The lower whole brain and cortical gray matter OEF values in MS are consistent with previous MRI and PET studies, which may represent a unique tissue injury mechanism underlying progressive demyelination or neurodegeneration in the MS brain. Lower OEF in deep gray matter may be associated with the tissue loss in those regions. For instance, the lower OEF in thalamus, a central link for cortical and subcortical circuits, may be related to previously reported thalamic nuclear neuronal loss and atrophy. So this is all I prepared regarding QSM plus qBOLD approach for OEF mapping. And thank you.